tone is so lame. I wish I had some knowledge about digital signal processing to help me to acquire a much better tone. What the heck? How's it going, dude? In case you haven't already put two and two together, I'm you from the future, so cool are you. And I brought this device that will help you to get that tone that you have been looking for with ease. What in the name of Mike? How did you get here? Oh, you know, just your regular everyday stuff like the multiverse and opening a portal. It was actually quite easy. Alright, show me how this new technology that you've brought works. Cool beans! Whoa, you really are me. Cool beans is my phrase. First, let's start off with the EQ settings. So you can see right here we have the bass, mid, and the treble. These are actually just filters being used for DSP techniques right here. So if I were to play the lowest note and adjust the bass, and get rid of the treble and the mids, you'd hear it to be much more defined as bass. Listen. Right there. It's much more of a deep sounding note. Where then if I were to get rid of the bass, up the mids, and not as much treble, play another note, you can hear it's hard on the mids right there. Play the lowest note, it doesn't have the same punch that it once did, especially when you turn this all the way down. It's a very different sound. Now, finally, we can have our treble all the way up, crank that. And if we were to have our mids down here, the bass down, it sounds kind of weird, especially if you were to play the top notes, where it's very, very pronounced. Now, the optimum tone is balanced, as all things should be. So if you put these like this, that's more of an entire tone. So now it's time to explain how these knobs do their job. The first question we have to answer is, how does a guitar convert an analog event like the vibration of a string into a waveform to be sent through this cable to the amp or the pedal? The answer lies in the pickups of the guitar, the magnetic coils of wire containing 6 pole pieces for 6-string guitars, 7 pole pieces for 7-string guitars, and so on. The mechanism of electromagnetic induction is used to convert the mechanical vibrations of the metal strings into electric signals. This can be described with Faraday's Law of induction, which explains how a magnet sweeping through a magnetic field induces a current in the circuit. So Faraday's Law can be expressed as epsilon equals negative n d phi over dt. So where this is what they would call the induced EMF or the induced voltage, n is the number of turns in the coil of the inductor, phi is the magnetic flux, and t is time, like normal. So before we start doing any derivations to try to reproduce this equation, it would be best if we draw a diagram of the situation that we're getting at. So here's one of my pickups, EMG. And here is the string or wire going through it, which in our case we're going to be treating as a magnet. So we have our magnetic field lines going into the page right here, and pretty much all around this wire. So that's super important, because when you give this wire a velocity in either direction, it doesn't matter, it's going to generate a magnetic field. And the thing that's super important about that too now is that the angle between the magnetic field and the motion of the wire is 90 degrees, which will prove to be very useful later. So the reason any of this works is because the strings on the guitar are magnetized, because they're often made of iron, copper, nickel, or cobalt, or materials like that play well with magnetic things. So in order to derive Faraday's law, we need to note that the charge moving with the string experiences an upward Lorentz force and will move towards the top of the string and accumulate there, implying that the negative charge gathers at the bottom. Then the difference between the bottom and the top creates an electric field. With our string here being of length L, the voltage between the ends is as follows. So if I'm going to scroll down to give myself more room, it's going to be E, because our induced voltage is length of the string times E, the E field. So now we need to remember that we have this equation too, V cross B, which we're going to substitute in right there for E. So epsilon equals L V B sine theta. Now, what did we agree that theta was? That's 90, so sine of it is just 1, which is super convenient and helps to reduce this equation to epsilon equals LVB, which is the Hall's effect. It's an expression of the Hall's effect, which is super cool that it comes up here, even though, you know, it kind of is like the definition of the Hall's effect. So now we need to note that LV equals dA over dt, because it's representative of the change in area with the time. Because you can, like, you know, imagine the string, like on our pickup right here. Oops. You can see it like moving from here to here, like that, and then here's the area that it's covered, and then in time interval dt. That's going to be very important, because it's just a box, you know, it's a V and L. Okay, so the reason that's important is because now we're going to introduce magnetic flux as d phi equals b dA. This comes from the integral expression for the magnetic flux. So now we're going to scroll down a little bit, get back to writing mode. Okay, so we have from earlier dA equals LV dt, okay, and then this could also be expressed as BVA equals BLV dt, okay, and then now this can be expressed as BDA equals epsilon dt, cool. And then now from this right here, the definition of magnetic flux, we have that dA is d phi over b. Okay, so now if we substitute this into that equation, we're going to be left with b d phi over b equals epsilon dt. So these cancel, and we're left with d phi equals e dt, or, you know, if you divide both sides by dt, you're left with this. So this is almost what we were looking for, but we need a negative sign here. And the reason that it's justified to put that negative sign there is because of Lenz's law, which states that the induced EMF makes a current flow that pushes against the change in magnetic flux. Now, the most important caveat of this equation is that there's no physical motion required to generate an induced EMF, but just a change of the magnetic field, which can be done through other means. In our case, however, the magnetic field is changing due to the oscillations of the string being plucked. So we're generating an induced EMF merely with some motion, which is pretty cool. Guitar pickups are a very cool thing. Now for the EQ knobs. The bass knob uses a low-pass filter, the mids with a band pass, and the treble knob with a high-pass filter. We worked with these types of filters and obtained the H functions in class, so I'll skip over the details for that. And the bandpass filter is essentially a combination of low-pass and high-pass filters. What the interesting thing is now that we turn our attention to is the gain knob. This is at the very heart of guitar, as it's responsible for the gnarly metal tone that we're all familiar with. And so I'm going to use octave, since I've acquired some samples of distorted and undistorted notes from the guitar, so we can compare their waveforms. So now on the computer I've recorded two samples of data. One of them, note 1, right here, is the undistorted tone with no gain applied. Note 2 is the distorted note with a lot of gain applied. So let's hear the difference before we go into octave and analyze them. Okay, so that just sounds like what you'd expect a undistorted guitar tone to sound like. And now number 2. So there is a large difference between those sounds, obviously. So now what we're going to do is we're going to go into octave and see what the difference between those two sounds is. So X1 is audio read note 1.wav, and X2 is just going to be the second one. So now let's plot them. Now keep in mind, we don't have them being plotted with respect to any time or anything. We just have them being plotted with respect to which sample number it is. So plot 1 right here, I'm going to bring it in from the other screen, looks, you know, like you'd expect a note to look like. It's pretty intense looking, but you can definitely see that it dies out over time. Now, whereas if we're to plot the one with the gain, you can see that it does not die out. And as a matter of fact, it stays about the same amplitude for the whole time because the gain is constantly being applied to it. So if I were to plot them in the same graph, so you can totally see that the gain one just totally eats up the other one for breakfast. It's like no competition at all. It's much louder, and it's also just much more intense. Now, we can close that graph. Now, if I'm going to take the Fourier transform of these, we might get a strange result, or you might have been expecting it. So let's plot the first one. So we can see right here that it's centered around the middle, which is as to be expected. Okay, but you can see the scale on the bottom is 200 to 400. If we were to plot the second one, however, it's still centered around the middle, but the scale changes a lot. And that's because there's a lot more frequencies from different places coming in there. It's not just the natural stuff, it's all the stuff being applied from, you know, all the noise that's coming in. So if we plot them on the same graph, you can hardly see the first one. But you can see that it's at the very center of the one that is inclusive of the gain, which is actually quite cool. And the arms that are spiraling out there are all part of that too, because those are the blue ones. It's really cool that those followed the same pattern. Okay, so now we can close that. And that's pretty much all for those signals. But, however, there's one more thing I want to do. If we're going to plot them, the original ones, and zoom in on it, you can see that it looks, you can still see the sinusoid in there. Like this going through down the middle. You can see it dying out over time for sure, but there's, you know, a decent amount of noise, but you can definitely make out the sinusoid in there. Now if we're to plot the one with the gain, what would happen if I were to zoom in? Let's see. Well, it's definitely a lot more chaotic, and I'm looking and I can't find that sinusoid anywhere. So if I'm going to auto scale and go back, let's try to look at the end. Right here. There would I mean, you could hardly make it out compared to the other one. It's very cool though. Very cool stuff.
So that's it. That's all you needed to know. Now, come with me for one small surprise. Now, I must bequeath to you these glasses so that you may carry on our legacy to the next generation. Why, thank you. I'm so very honored to have these glasses. Now I possess the power to bend time and space. How's it going, dude? In case you haven't already...